1.1, linear equations. Okay, so we are now done with reviewing. Well, that's a lie. Okay, we did chapter R, which was purely review. What you're going to find is that for a large portion of this course, you're going to be reviewing stuff that you did previously in MA 115 or in another course, and we're just going to be kind of expanding upon it at certain points. So don't be too surprised by that. So now we're going to talk about linear equations, but to start with that, what is an equation? Because we've dealt with radical expressions, we've dealt with rational expressions. So an equation is just a statement that two expressions are equal. So as soon as you put an equal sign in there, we now have an equation. You could have an expression x squared plus 3. That's an expression. You can have another expression x minus 2, an expression. As soon as you put equals and say those two expressions are equal to one another, now we have an equation. Whenever you have an equation, there is a solution set. The solution set is all numbers that satisfy the equation. So yes, we're going to be in solving. You also deal, when you're dealing with equations, you can have equivalent equations. Equivalent equations are ones that are functionally the same, or the solution set is the same. Such as, let me get this out of the way here. X equal to 7 is equivalent to 2x equal to 14. Because x equal to 7, if you make x equal to x be 7, then 7 is equal to 7. If you make x be equal to 7, then 2 times 7 is 14, is equal to 14. So equivalent equations are those that share the same solution set. Why do we care about that? Because we're going to deal with the addition property and the product property, which basically says that if you have an equation A equal to B, and you add the same thing to both sides, and of course remember we're dealing with real numbers at this point, if you add the same thing to both sides of the equation, then you have an equivalent equation. A plus C is then equal to B plus C. If I have 5 equal to 5, and I add 2 to both sides, 5 plus 2 is equal to 5 plus 2. Okay? When you deal with numbers, it kind of seems too obvious, right? It just says that if you have an equation, if you add the same thing to both sides of the equation, then you have an equivalent equation. It's not the same equation, but it's an equivalent equation. The product rule says if you have an equation A equal to B, if you multiply both sides by the same thing, then you have an equivalent equation. If A is equal to B, then A times C is equal to B times C. 5 equal to 5, 5 times 3 is equal to 5 times 3. Again, when you throw numbers in it, it's just obvious. We get a little thrown off when we look at variables. Now, subtraction and division are just an extension of addition and subtraction here. If you subtract the same number from both sides, you have an equivalent equation. If you divide both sides by the same number, you have an equivalent equation. So all of these things just come together to allow you to manipulate these equations so you can solve the equations. Now we're talking about linear equations specifically at this point in time, and so that means we're not going to be dealing with second, third, fourth, or higher degree equation. A linear equation is a first degree equation. It can have one variable, or it can have numerous variables. But all of those variables will have at most a degree of 1. So I can have y equals mx plus b. Oh, wait a second, that's a line. Linear equation, right? Y and x are variables. M and b are placeholders for constants. They're variables too, but they're placeholders for constants. So if you have y is equal to 3x plus 2, first degree variable, creates a line. Now many times we deal with single variable equations, other times we deal with multivariable. There we had 2 variables. Or we can also deal with just 1 variable. So how do we solve these equations? Well, let's have that. Let's go for negative 4 times 3x minus 5 is equal to 3 minus, go for 8x plus 7. Talk about going for the gusto, right? All we're trying to do if we're going to solve this equation is we want to get x by itself. And we're going to use the addition property, the multiplication property, subtraction and division as an extension of those to do that. So if we're going to do that, I need to get this by itself, I need that by itself. So I'm going to distribute through is the first thing I'm going to do here. So I'm going to negative 4 times 3x gives me negative 12x. Negative 4 times negative 5 gives me plus 20. This is equal to 3. I'm going to distribute that negative through. Minus 8x minus 7. And just remember, we tend to say negative or minus however it's helpful to us. This is actually 3 minus all of this. But when I distribute it through, it's like saying 3 minus 1 times this. We can distribute that negative 1 through, so it's negative 8x, negative 7. Now that we have this, we can combine like terms, get the variable over to the same side and get it by itself. So here I've got something to combine over here, so I'm going to make this negative 12x plus 20. I'll leave it as it is. But I've got 3 minus 7, so let's make this negative 8x. And 3 minus 7 gives me minus 4. Well, let's get the x's over to this side. Well, we'll do it over to this side. I have a tendency, I like to go the direction that makes the coefficient positive, but you don't have to do that. You just have to be careful if it's negative that you remember to do all the steps to get rid of it. But many people don't like to put the variable on this side when they're solving. You'll get used to it with time. Put it over there. It doesn't matter which side you solve it on. Or what I may do, and this even people get even more upset about, is I may solve it over to this side, but move it over to the other side so that I can keep my x on the left-hand side. We're not going to do that right now. We're going to get the x's over to the left-hand side, so I'm going to add 8x to both sides. Remember, addition rule says if you add the same thing to both sides, you get an equivalent equation. So I'm going to add 8x to both sides. Negative 12x plus 8x gives me negative 4x. I'm going to subtract 20 from both sides. Negative 4 minus 20 gives me minus 24. I want to get x by itself, so I'm going to divide both sides by negative 4. Negative 4 divided by negative 4 is 1, so we have x. Negative 24 divided by negative 4 is 6. So we have x equal to 6. So it's just a matter of taking it a piece at a time, doing each of the steps to get a result. So we came out with x equal to 6. Okay? So that wasn't too painful. It looked bad to begin with, but overall it wasn't too bad. Now, when we're finding solutions to these linear equations, there are a few things that can happen. The first is we can have an identity. An identity is one in which all values make the statement true. So for an identity, basically the statement's true no matter what you put into it. I'm just going to write that as all numbers work. Second thing that can happen is we can have a conditional statement. For a conditional statement, some numbers work. So you will find some that work and some that don't. So whether you can come up with a true statement is conditional upon which values you plug in. The third thing that can happen is you can have a contradiction. In a contradiction, there is no number that works, so no numbers work. So you got all, some, or nothing. In an identity, no matter what value you plug in, it's going to work for it. For a conditional equation, certain values will work, certain values will not. And for a contradiction, no values will work. Well, let's take a quick look and see what we can do with this. So, an example of an identity would be 2x plus 4 is equal to 2 times x plus 2. If we distribute this through, we see that 2x plus 4 is equal to 2x plus 4. So obviously, any value I plug in for x on this side is going to work on that side since it's the same expression on either side. So that would be an identity. I can plug any value in for x, and I'm going to get a true statement. For a conditional statement, 5y is equal to 10. There's only one value I can plug in for y that will make this a true statement, when y is equal to 2. 5 times 2 is 10. I can't plug in any other numbers and have it work. Whereas a contradiction, z is equal to z plus 3. Well, let's put the z, if I put the z's on the same side, they just disappear, right? I've got a z here, a z. Obviously, a number can't be equal to itself plus something. If I add or subtract a number from some value, I'm going to get something different. So that's a contradiction. There is no value of z that will make this statement true. But what really happens when I have these situations? When I have an identity, as I go to solve it, I'm going to end up with a true statement. I'm either going to have the variable equal to itself, or I'm going to have some constant equal to the same constant. In fact, if we look at this, if I were to start to solve this, I go, okay, well, let's subtract 4 from both sides. I have 2x is equal to 2x. Now I divide both sides by 2. I get x is equal to x. Right? I end up with a true statement. X is equal to x. 7 is equal to 7. Negative 356 is equal to negative 356. So a true statement, we come up with something equal to itself if we have an identity. Conditional statement, y equal to 2. If we have a conditional statement, we will come up with a value that works. The variable is equal to such and such. And that's what we get here. Y is equal to 2. So I'm going to put that as variable equals some constant. And that's a true statement. It's going to create a true statement. It's going to do that is equal to some constant. A contradiction, what's going to happen is you're going to end up with a false statement. If I come over here and I subtract z from both sides to get it over to the other side, I'm going to have z minus z is 0 is equal to 3. Well, that's not true. That's a false statement. So those are the possibilities. Let's try some and see what happens. Okay, what about 6x minus 9 is equal to 4x plus 13? And we want to determine whether this is an identity, a conditional statement, a conditional equation, or a contradiction. So what are we going to do? We're going to get the x's on the same side, get the constants on the other side. So subtract 4x from both sides. 6x minus 4x gives me 2x. Add 9 to both sides. 9 plus 13 is 22. Divide both sides by 2 and we get x is equal to 11. X is equal to 11. Therefore, this is a conditional equation. Now, we should always check and see whether it actually works. So you solve and then you check. So checking this, we would plug it in, meaning plug our solution, into the original equation and see how it works. 6 times 11 minus 9 equal to 4 times 11 plus 13. 6 times 11 is 66 minus 9. 4 times 11 is 44 plus 13. 66 minus 9 is 57. And 44 plus 13 is 57. So yes, that did check. Now, let me just point something out to you so you don't fall into the trap. This did not make it an identity. This is you checking. You went through this, you solved, and you found that it was a conditional statement. There was a value that made this statement true. Conditional statement. This is just the check. This is supposed to come out the same every single time. So don't look at this and go, oh, it's an identity. Now, I say that and you may be looking going, well, Mr. Davis, obviously you already found it was conditional. But it's a regular occurrence. I see people, they do that, they're being good and they do their check and they come up with this, they come up with a value, x equal to 11, they go through this, do the check, and they go, oh, look, it came out to be a true statement, it's an identity. No. It is only a true statement when x is equal to 11, therefore it is conditional. So don't fall into that trap. So let's try another one. 10 plus 14x is equal to 7 times 2x plus 5. Okay? So, first thing I would do is I would distribute the 7 through. So 10 plus 14x is equal to 7 times 2x is 14x. 7 plus, did I write that down correct? Yep, just making sure. 7 times 5 is 35. So we're going to get them onto the same sides, constants onto the same side, variables on the same side. So let's subtract 10 from both sides. So I got 14x is equal to 14x. 35 minus 10 is 25, so plus 25. Gonna subtract 14x from both sides. I think you can see what the problem's gonna be right there. 14x minus 14x is 0 is equal to 25, and we have a contradiction. A contradiction. So be careful about that. The reason I did a quick check to make sure I wrote it down correctly was just I saw this, and if the 2 had been outside, then this would have been an identity. So I was just making sure that that wasn't the case. So we have a contradiction here. Let's try another one. We have another prepared problem. What do we have? Negative 3 times 2x minus 1 plus 5x is equal to 3 minus x. Okay, so again, I would distribute through first, so negative 6x plus 3 plus 5x is equal to 3 minus x. Combine like terms, negative 6x plus 5x gives us negative 1x, so negative x plus 3 is equal to 3 minus x. Let's subtract 3 from both sides. Negative x is equal to negative x. Divide both sides by negative 1, and we get x is equal to x, and we have an identity. Well, is that the only way we could have done it? No, we could have done it a number of ways, but just pointing out, if here, at this point, we had decided to move the x's first, we could have added x to both sides, and we would have had 3 equal to 3, which would make it an identity. Right, because we still have a true statement. So remember, an identity, you will end up with a true statement, a constant equal to itself, or the variable equal to itself. For a conditional equation, you will end up with the variable equal to some value. And for a contradiction, you will end up with the variable equal, well, I should say a constant equal to a different constant. So you end up with a false statement. Okay, one last thing that I want to include in this. Let's solve for a specific variable. So solving a literal equation. A literal equation just means you've got variables equal to other variables. So let's say we have S is equal to KR squared plus KRL. And I want to solve for K. So I want to solve this for K, so I want to get K by itself. Well, what am I going to do here? Well, I have KR squared plus KRL. can't I factor out the k and leave the rest of the stuff there? So I can say s is equal to k times r squared plus rl. Remember, we don't have to necessarily factor out the greatest common factor. We're trying to get k by itself. So don't factor out kr and give yourself kr times r plus l, because you're still going to have to get rid of that r at some point anyway. We just want to pull the k out. Now that we have that done, how do we get rid of this? K times something. To get rid of it, we divide. So we divide both sides by r squared plus rl. So s over r squared plus rl is equal to k. And we have solved this literal equation for a specific variable. So it doesn't work any differently than if you have numbers. The only thing that really comes out different with it is when you're dealing with solving for a specific variable, your equation doesn't always get nicer. Notice that when we were solving and we were dealing with numbers and you only had one variable in there, your equation got smaller and smaller and smaller until you got to an identity, a conditional equation, a conditional result, or a contradiction. Whereas you can see here, the equation didn't get any prettier per se, we just changed it so it was equal to a different variable. A different variable had been isolated. So that's the one big concern of dealing with these when solving for a specific variable is it doesn't necessarily get prettier, and that kind of makes it less fun than dealing with the numbers where we don't, every step we go, we're going to get it smaller and smaller and smaller until we get to the solution.